Hello, this is an overview about the paper titled "A Review of Current Techniques for Robotic Arm Manipulation and Mobile Navigation" by Dr. Balasubramanian Chandrasekaran and Troy Sivasankar. The topics that will be presented in this overview will be about the motivation for writing this review paper, the review findings, and future possibilities regarding this review. The motivation for writing this review paper was for the purpose of gathering information that would provide insights into high-level architecture, which would lead to possible improvements, unique and/or hybrid approaches for robotic arm manipulation and mobile navigation. The first paper in this review is titled "Kinematics Analysis and Trajectory Planning of 6 Degrees of Freedom Robot." This paper proposes combining a H2O humanoid robot arm trajectory planning method with swarm optimization and genetic algorithm, which would create a hybrid algorithm that optimizes trajectory planning. This paper also includes the Denovitt-Hartenberg model for forward and reverse kinematics. It uses the Monte Carlo method in MATLAB to calculate the workspace, and it uses interval notation for uncertain geometric parameters. It also uses point-to-point and continuous path methods for motion trajectory simulation. This paper also presents quintic polynomial algorithm in MATLAB, which is used to determine the joint space interpolation for every 50 milliseconds. Formulas, calculation results, and graphs, in addition to simulation diagrams, are provided to show the feasibility, to confirm accuracy, and to provide an in-depth description of the proposed work. Practical implementations in a real-world scenario would enhance the credibility of the proposed work. The second paper in this review is titled "Robotic Gripper Arm System with Effective Working Envelope." This paper proposes the addition of an extra degree of freedom, which results in a 7-degree of freedom robotic arm that improves the reach and efficiency of pick-and-place maneuvers. In this paper, the robot accomplishes these improvements by reaching any position within the workspace by using forward and inverse kinematics and only 3 links. This paper also states that redundancy of arm configurations is determined by kinematics calculations. However, these redundancy configurations are examined for operational efficiencies and dynamic effects. It also states that algorithms for this research were used to obtain efficient trajectories. Therefore, mathematical analyses of these algorithms are presented. The decision-making algorithm of the functionality has the robotic arm reach for the closest attainable point whenever the intended object to be picked up is out of range for the robotic arm. The comparative analyses between the previous work and the proposed work show that the proposed work is more accurate and more efficient. The third paper in this review is titled "Robot Arm Manipulation Using Depth Sensing Cameras and Inverse Kinematics." This paper proposes improved user interface features such as using hand gestures and voice commands that are used to determine the intended goal point for the gripper or end effector, and then to use inverse kinematics, with one exception, to perform maneuvers to reach the goal point. It states a depth camera reads the relative depth of a human hand in relation to the lenses and performs inverse kinematics to control the robotic arm accordingly. The researchers state that this method for controlling robotic arms is less expensive due to requiring less training than conventional training means. The fourth paper in this review is titled "Design and Development of an Omnidirectional Mobile Manipulator for Indoor Environment." It proposes mounting a manipulator upon an omnidirectional mobile base for improved functionality and presents actual experimental results from a controlled environment. It states that the manipulator dynamixel motors are interfaced with Java spread spectrum of libraries and APIs for communication. An Arduino board is connected to Raspberry Pi 3 for robot operating system kinematics to control sensors, motors, etc. MATLAB Robotic System Toolbox is interfaced with the robot operating system. Some future possibilities and considerations for each of the four papers in this review are: for paper 1, practical implementation in a real-world scenario would enhance the credibility of the proposed work. For paper 2, the researchers explain that future work can be in converting the robotic arm into a double arm and improving kinematic control. For paper 3, the researcher suggests that future work will be to include spherical and prismatic joints, not only cylindrical joints, to experiment with remote control operation of the robotic arm, to develop an end effector that will be able to grasp non-uniform and unmolded objects, and that actual tests with a real robotic arm will be performed in the future. For paper 4, map renderings and navigations were shown. However, actual object manipulations were not. These are the references.